Hey there, everybody. We are going to talk about bonds today. So, chemical bonds. Specifically, today is ionic bonds. We're going to learn what they are, how they form, how to write their formulas, how to write names for them, how to take the names if you're given those, and write the formulas for them. So, there is a lot going on today. Feel free to pause it, take a break, and come back. It is a lot. It's a lot for me to say all at one time, much less to learn. So feel free to take a pause here and there where you need one. And I'm just going to go ahead and get started. All right, here we go. So, chemical bonds. Let's rehash what we already know. We already know about atoms, right? This tiny indivisible piece of matter. We know that's not true. They're divisible. We have talked about their electron shells. So we talked about how the atomic number is the number of electrons, right, in an atom. And this might vary in the amount of energy they possess because they could be in the lower levels or they could be in higher levels. Um, and those electrons in the outer level are what's going to determine the chemical properties of the atom. So sorry about that. Electrons are placed in shells according to rules, which we've already discussed as well. We have talked about how hydrogen, that first level, that s orbital, will only hold 2 electrons. If you look at carbon here, it has 2 energy levels. The first level holds 2. The second level could hold up to 8, but since carbon only has 6 to put in altogether, you put 2 in this shell and then you have 4 out here. Now to fill that shell would take 8. So you can see there's 4 places where an electron could go. That's going to mean there's 4 places where carbon wants to form bonds. Hydrogen just has 1 place that it wants to fill, right? Nitrogen, here's the Bohr model for that. You can see there's 1, 2, 3 missing electrons from its valence shell. So it's going to want to do something to fill those 3, right? And oxygen has 2 open spots. So it's going to want to do something to fill those. That's what bonding is. They're either going to share, transfer, or, do whatever they need to do to get those outer levels full, those valence levels full. So somebody like carbon might gain 4 electrons. Nitrogen, on the other hand, might gain 3 electrons. Oops, something else went off the card there, sorry. So electrons, all atoms have their different electron configurations, which means they bond differently. So we've already looked at our periodic table of elements, right? And you're going to want to make some notes on that periodic table as we go through this today. So if you need to pause this and go get your periodic table, you might want to do that. If you look at Bohr models and you line them up, so we've taken out the transition metals here. This is just the first 2 columns. So these are your alkali metals, your alkaline earth metals. Then we jump over here to the boron group, carbon, nitrogen, oxygen. But to just look at the transition metals for now, notice all of these have 1 in their outer shell. They're all going to want to lose that 1 electron. These all have 2 in their outer shell. They're going to want to lose those 2. These have 3 and want to lose them. So all these are tending to lose their electrons. Now, when you get over here, they're really close to being noble gases. These are the noble gases. So these guys want to gain electrons. So you're going to gain 1 electron and be full. These are going to want to gain 2 to be full. These are going to want to gain 3. Now in the middle here, carbon. They could gain or they could lose. Probably going to be more likely to share things. We'll talk about that next week. Covalent. So if you look at the dot structures, that's what's going to lead to these properties. So here, everything in the first column has just 1 dot, right? Meaning if they got rid of that dot, they could maybe go down to their lower shell, their noble gas core, right? Here they've got 2 dots. These have 3 dots. So these Lewis dot structures that we learned how to draw previously are going to come into play in helping us see how things bond. We're going to talk about ionic bonds, covalent bonds, and metallic bonds. Today, the focus, just ionic. Believe me, it's enough for one day. So let's take a look at this and say, what would be the electron dot formula for this? So this would be the electron dot formula, sorry, for which of these things? So if it's only got one dot, then we're like, oh, it's only going to have one electron. It could be sodium. Yep, that's in the first row. Could be potassium. Could it be aluminum? No, that's going to have 3. Here's another one. This one has 1, 2, 3, 4 dots. 5. There you go. I was like, where's the other one? 5 dots. So what would that one be? Could it be boron? Probably not. Nitrogen? Probably. Phosphorus? Yeah, could be either one of those. All right. Ionic bonds. These bonds here's their definition. They form between 2 ions and they involve transferring electrons. Okay, so it's important that you understand that 2 ions, at least 2 ions, and they transfer electrons. Very, very important word there. Electrons leave one and go to the other. So, ionic compounds happen when a metal meets a nonmetal. So remember on the periodic table, you have the stuff on the left-hand side, those are metals. Metals like to lose electrons, right? It's easier for them to lose 1, 2, 3, go down to their noble gas core. So when you lose electrons, you're forming a positive ion. Remember, electrons are negative. You're then going to have more protons than you do electrons and be positive. So group 1 metals tend to make +1 ions because they lose 1. Group 2 metals tend to lose 2 and make +2 ions. Group 13, so that's over at the boron, aluminum, those over there, they tend to lose 3 and make a +3. You might want to write that on your periodic table. We'll get to it in a minute. So sodium, with that 1 electron, wants to lose that outer electron and go down to its noble gas core so it can be like neon. When it does, so originally here's the atom. So you've got to get used to, this is going to change the name of the thing here. So this is a sodium atom, right? Same number of protons as electrons. This is a sodium ion. Now it has 11 protons still, but it has lost an electron, so it has a +1 charge. Overall, it is positive. It has one more positive than it does negative. So we call this a sodium ion, where this was a sodium atom. So that's going to be really important. Listen to those name changes. This is a magnesium atom, right? 12 protons, 12 electrons. 2 valence electrons. This is a magnesium ion. This has 12 protons, but only 10 electrons, so it has 2 more positives. It has a +2 charge. So again, typical ions that form with the positives. Group 1, they all tend to make +1 ions. Group 2, all tend to make +2 ions. Group 13, aluminum, +3. So you might want to put that on your periodic tables. Let's go through a little learning check here. The number of valence electrons in aluminum. Pause it if you need to think about it, and I will give you the answer. So the valence electrons in aluminum are 3. The change in electrons for the octet, what's aluminum going to do if it has 3 valence electrons? It's going to want to lose those 3. And then the ionic charge, if you're losing electrons, you're positive. So if you remember the cation walks into a bar joke, lost your electrons. Are you sure? Yeah, I'm positive. So lose your electrons, you're positive. All right, let's give the ionic charge for each of the following. So if you have 12 protons and 10 electrons, what's your charge? That's right, you're +2. If you have 50 protons and 46 electrons, what's your charge? Well, you have extra positives, so you're going to be positive. You have 4 extra positives, so +4. 15 protons, 18 electrons. What's your charge? If you have more electrons, you're going to have to be negative. And if you have 3 or more electrons, you'll be -3. All right. Ions from nonmetals. So the metals tend to be positive. They're electron givers. Now you have the other side of the periodic table where the nonmetals are. So your groups 15, 16, 17 over on the right-hand side. Those are nonmetals. They're so close to having their octet, they want to just beg, borrow, and steal to get some extras. When they do steal them, they're going to become negatively charged because they're going to have more negative electrons than their positive protons. Oops, too far. So here is an unpaired electron right here. Sorry, that should point right there. You've got fluorine here. It's got 7. Man, it really wants to pair this electron up. So it's going to steal an electron from somebody, fill that hole in its shell. But now it'll have an extra negative compared to its protons. So it had 9 protons. Now it's got 10 electrons. It'll have a -1 charge. And here, the names are going to change. So in metals, the name went from atom to ion. But in nonmetals, we're actually going to kind of change the name a little bit. This is going to be called fluorine. This will be fluoride. Okay, so an IDE is going to tell you it's an ion now. That's coming up in the naming. All right, so what do we know about ionic bonds? They happen when a metal and a nonmetal get together, and the reason is they have those very different electronegativities. So metals are like, I don't even really want the electrons I have. Nonmetals are like, oh my God, I really need another electron. They have those really high electronegativities they want to steal. Metals have very low electronegativities. The difference there means the electrons are going to transfer. They're going to leave the metal, and go to the nonmetal. That is a big deal, that transfer. Once they do transfer, then you're going to have these charges, these positively and negatively charged things. And what do opposites do? They attract. So once they're charged, they're going to pull together and hang out together. Now you have an ionic compound. These charges are going to mean that they're good conductors if they're melted or dissolved. So a solid, not so much. But if you melt them or dissolve them, those little charged particles are free to move around, and it makes them good conductors, right? And they're going to tend to have high melting points. Again, it's because of the structures they form with those positive and negatives coming together. They're like little magnets holding those ions together, which means it's going to be hard to melt them. It's going to take more energy to pull them apart and melt them. Some examples might be sodium chloride, calcium chloride, potassium oxide. All of those have a metal and a nonmetal. Metal, nonmetal, metal, nonmetal. So this used to have an animation, but it doesn't work in Google Slides. So what should happen here, the sodium electron is going to leave the sodium and go over to the chlorine. So again, my animation not working there. So sodium, this electron is going to leave sodium, go to chloride. Then you have, notice how sodium got smaller. We talked about they get smaller, right, when they go to the positive ions. It sheds that outer shell, and it's going to hang out with this chlorine ion because you have a positive and a negative. So now they want to hang out together. This is an ionic bond. You have an electron being transferred. You have two ions now holding together. And why they're so strong, why they have those high melting points, is these structures that they have here. So if these are the sodiums and these are the chlorides, that's how they bond. They're like sodium chloride, sodium chloride, sodium chloride. So each little attraction between all of these little ions is like holding together like magnets. So to get them to start moving apart, to melt them, you would have to add a lot of energy to pull those apart. So high melting points. Now, Most of what we've mentioned so far have been monoatomic ions. So monoatomic means one atom. So just straight off the periodic table, lithium is a monoatomic ion. But some ions are made from more than one atom. Those are polyatomic ions. Now, I'm sorry, but there's just some things you have to memorize in chemistry. And I'm giving you a list of, I'm giving you one paper with tons of polyatomic ions in it. That's a reference sheet. But I'm giving you about 10 that you should just memorize. It will just make your life easier because when you see a name and you see hydroxide, I don't want you to think that that's hydrogen, right? I want you to know that that's a special polyatomic ion called hydroxide, and you need to know the formula for it. So, more on that in a different video. Now you've got cations and anions. So, cations are the positive, anions are the negative. You get them together, you get a compound. So, in this case, sodium chloride makes sodium chloride. Now, the compound should be neutral. That means all the charges should balance out. This is a plus one, this is a minus one. That means this guy lost one electron, this guy gained one electron. Now they make a nice little happy couple in 1-to-1 ratio. So this is its empirical formula, that lowest whole number ratio that they can combine in. Oops, too far. If you haven't already put these on your periodic table, you should. Everything in this first column tends to make a plus 1 charge. Everything in the second column tends to make a plus 2. Over here, they tend to make negatives. So, of course, noble gases aren't doing anything, but the halogens tend to make negative 1s. The oxygen group, negative 2s, negative 3s here. Now, what about the transition metals? Oh my goodness, they're going to be a whole other problem. They can do a lot of weird stuff. So just some of these can make 3 or 4 different charges. So we're going to have to talk about those when we name them. They're going to have their charge in their name. But there are a few that always do the same thing. So you might want to make a note on your periodic table. Zinc's always a plus 2. Silver's always a plus 1. Cadmium's always a plus 2. Aluminum's always a plus 3. Other than that, these guys in this area, well, you're going to need a charge in their name. Metal atom can transfer an electron to a nonmetal. This results in the two being held together. We've said right now, like opposites attract, magnets, right? The fancy name for that is electrostatic forces. So those opposite charges attract each other. So again, here is one with a polyatomic ion. So in this case, you've got ammonium, which is this ion, NH4. It's on the list of things you need to just memorize, not to be confused with ammonia. Ammonium, 4 syllables, 4 H's, okay? So ammonium is a plus 1 ion. It'll combine with here, in this case, chloride, which is a negative 1. So you have ammonium, chloride, ammonium, chloride, ammonium, chloride, all in making those same tight network structures for that ionic bond. But this is a polyatomic ion because it has more than one atom involved in it. They're held together by covalent bonds inside this polyatomic ion. And then these two are held together by an ionic bond. Okay, so some ionic compounds. Now we said that the charges have to balance. So here, calcium has 2 electrons to lose, but fluorine only wants 1 electron. So it's going to take 2 fluorides to bond with that calcium. The result would be calcium fluoride. So for every 1 calcium, you'll have 2 fluorides bonded to it. Okay, so that should hopefully make sense to you. You have 2 electrons to give away. This guy can only take 1, so we put this coefficient here in the front. That means I need 2 of these. And then when we write the formula, we write calcium, Ca, There's only one, so no number. F2. This 2 is a subscript, and that's telling me I need 2 of these fluorides for every 1 calcium. This is the empirical formula, okay? That's the lowest whole number ratio that you have to have in an ionic compound. Oops, too far. So here's magnesium, and here's nitride, okay? This guy has 2 to give up. This guy wants to take 3. So if I just put one magnesium with the nitrogen, it's not going to be happy. It's going to want another one. So it's going to need another magnesium to come in, right? And then there's going to be too many electrons, and you're going to need another nitrogen. So there's an easy way to do this called crisscross. And when I have you in the classroom, we'll go over some of these a little bit more detail. But crisscross method says this number is going to tell you how many magnesiums you need, and this number will tell you how many nitrogens. So when I do crisscross, they become the subscripts. You don't worry about the negative or the positive. You just take the 3. So for every 3 magnesiums, I'm going to need 2 nitrogens. So those charges will balance out if you think about, okay, each nitrogen has 3 negatives. If I have 2 of them, I have a total of 6 negatives. Each magnesium has 2 positives. If I have 3 of them, I have 6 positives. 6 positives, 6 negatives, we're all balanced out. So that's magnesium nitride. Notice now we say the nitride. It's not nitrogen anymore, it's nitride. Once your nonmetal becomes an ion, it ends in IDE. You drop the ending and add IDE. All right, try this one. Okay. It's a little bit trickier. If you just did the crisscross, you'd wind up with 2 and 4. But if you heard me say empirical formula is the lowest whole number ratio. So when you crisscross these and you have 2 to 4, you have to reduce it down to its lowest ratio. Or you could just look at it and say, well, if I have a 4 being given away and this one's only taking 2, it's going to take 2 oxygens, right? So SnO4. Now, remember how we said the transition metals, we were going to have to include the charge in the name? That's what we're doing here. Tin, there's different types of tin. So this is a tin with a +4 charge. So we call it tin, Roman numeral 4. So tin 4, and then oxide. Okay, I know, it gets confusing fast. If you need to pause, go back and rewind, feel free. All right, formulas for ionic compounds are determined from the charges. So the charges have to balance. In this case, you have sodium, you have fluorine. Now, once they become ions, sodium doesn't change its name, it's still sodium, but fluorine becomes fluoride. So you have sodium fluoride. It's a 1-to-1 ratio. Everything's balanced. So here are some common cations and anions. So hydrogen, notice it could be hydrogen if it loses an electron. If it gains an electron, because remember, it only takes 1 to get it to its noble gas state, then that's hydride. Okay, there's lithium, sodium, potassium. Everybody else just keeps its name, right? The ones that don't require a Roman numeral are the ones that are always the same. The Roman numerals are going to be the transition metals that can be different things. Over here, your anions, notice fluorine becomes fluoride, chlorine, chloride, bromine, bromide. So you oxygen, oxide. You're ending it in IDE. All right, let's try writing the formula for an ionic compound between barium and chloride. So you've got barium with its +2, so it's giving away 2. Chlorine can only take 1. So we're going to need to have 2 chlorines to take up those 2 electrons. So crisscross, 1 barium, 2 chlorides, BaCl2. All right, let's try. I'm going to go through this. You can pause before I give you the answer so you can try it for yourself. Write the correct formula for the compound. Okay, so Na and S with a -2. So sodium sulfide. What's the formula for it? Na is a 1, so that's going to mean 1 sulfur, 2 sodiums. So Na2SB. Okay, aluminum chloride. So aluminum plus 3, chloride -1. It's going to mean 1 aluminum, 3 chlorides. Answer A. Then you've got magnesium nitride. So magnesium's a +2, nitride's a -3. So 3 magnesiums, 2 nitrides. Boom. C. Okay, hopefully you're doing good. All right. Now, a binary ionic compound just has a cation and an anion. So no polyatomics here, just made of 2 things. So like a bicycle has 2 wheels, binary, just 2 ions. In order to name it, you just name the cation, then name the anion. So monoatomic cation is just the name of the element. So sodium is sodium, potassium is potassium, calcium is calcium. The anion, you take the root and add IDE to it. So oxygen is oxide, chlorine, chloride. Okay? And that's all you have to do to name a binary ionic compound. This is calcium chloride. Doesn't matter how many there are, it's just calcium chloride. So try these examples. You can pause if you want before I give you the answers. Sodium chloride, zinc iodide, aluminum oxide. Complete the names of these. There's your sodium. And this was nitrogen, but it'll be nitride. Potassium, bromide. Aluminum oxide. Magnesium sulfide. Okay, now transition metals. Okay, here's where it gets fun. So, when you're naming something that has a transition metal, you have to include the charge in the name. Excuse me. So, copper could be a copper with a +1 or a +2. You could have iron 2 or you could have iron 3. That has to be in the name. If you don't know your Roman numerals, go review those real fast. At least 1 through 10, hopefully, or 1 through 12 for clocks. So, when you put the Roman numeral in, it's going to be in parentheses after the metal. Now, how do you figure out the Roman numeral? You're basically uncrisscross. Excuse me. You have to look at your formula and figure out what charge that metal would be. So, if this iron is bonded to 3 chlorines, each chlorine is a -1. So you have a total of 3 negatives. You have to have 3 positives. So this must be iron with a +3 charge. So it would be iron 3, Roman numeral 3, chloride. This copper is bonded to just 1 chlorine. So chlorine has a -1 charge. So that copper must have a +1 charge. So it's copper 1 chloride. Here's your tin. It's bonded to 4 fluorides. Each fluoride's a -1. So this tin must be a +4. Tin, 4 fluoride. This lead bonded to 2 chlorides. Each one's a -1, so lead must be a +2. So lead 2 chloride. Here's a tricky one. They both have numbers. You can do an uncrisscross. So the 2 goes with sulfur. Make sure that's correct. Is sulfide a -2? Sure is. So then this must be iron with a +3. Iron 3 sulfide. Now, believe it or not, it's actually kind of easier than when I was a kid. When I was in high school, a long time ago, there was copper 2 was cupric, copper 1 was cuprous, iron 3 was cupric, iron 2 was ferric and ferrous. See, they did the ick and the us, but the ick and us didn't necessarily tell you the number. It was just ick has a higher number than us, and you just had to remember what they all were. Remember we talked about plumbic and plumbus? So those are the two different leads. Ugh, that was terrible. This is actually a much easier system, so be glad you weren't having to memorize all these like I was. Complete the names for the following binary compounds with those transition variable metal ions. So take a second, figure it out. We'll do a couple together, and then we'll save the rest for when we're in class. So there's 2 bromines here. Each bromine is a -1 charge, so this must be iron, Roman numeral 2. Copper on 1 chlorine must be copper with a Roman numeral of 1, right? Here's oxygen. Oxygen, each one is a -2, but there's 2 of them, so you've got a total of 4 negatives, which means this must be 10,4 oxide. Uncrisscross this. Is the 2 right for oxygen? Yep. Then the 3 must be right for iron. Iron 3 oxide. If you uncrisscross this, the 2 is right for sulfur, so that must be 1 for mercury. Mercury 1 sulfide. I did them all. Okay, so polyatomic ions, again, you just need to memorize them because I don't want you to look and see nitrate and write just nitrogen, because if it was just nitrogen, it'd be called nitride, right? So there's nitrate and nitrite. Sometimes there's always a lot of times there's an ite and an ate. The ites have less oxygens, but that doesn't necessarily tell you how many. So the eights will have more. But like sulfate is SO4, right? So it doesn't matter how many it just has more than sulfite. So some things you just gotta memorize. And I gave you a list of 10 that you should memorize. You can make additional ones by adding hydrogen in there. So this is carbonate, right? CO3, it has a -2 charge. But if you put an extra hydrogen on it, it's hydrogen carbonate. Now it just has a -1 charge. This is dihydrogen phosphate. Okay, if this was just by itself, PO4 is just phosphate. SO4 is sulfate, but this is hydrogen sulfate. Again, you'll have your reference chart on tests and stuff, but your life will just be easier if you know at least the basic 10 of them. And that'll get you in the habit of looking closely at the names, because eights and ites and ide are all different things. So how do we write formulas? Well, start out by writing each ion. Write the cation first. Metal always goes first. Don't show the charges in the final formula. So the charges are going to help you balance it, but they don't go in the final formula. The overall charge has to be equal to 0. So your positives and negatives have to balance out. If the charges cancel, then just write the symbols. It means it's a 1-to-1 ratio. If not, then use subscripts to balance the charges. And sometimes you're going to have to use parentheses if you have more than one polyatomic. So let's look at that. Parentheses around the polyatomics if you have more than one. Important point here. And if you have a transition metal, you're going to have to use Roman numerals to tell us the charge. So let's look at this one. Sodium and sulfate. So here's sulfate. It's SO4. That's a polyatomic ion. Sulfate. has a -2 charge. If I'm balancing out the charges here with sodium, well, I'm going to need 2 sodiums, right? I'm going to need 2 positives because I got 2 negatives. So when I write the formula, I'll write Na2 and then just SO4 because I only needed one SO4. Let's try this one. Iron 3 hydroxide. So iron 3, that's going to be Fe with a +3 charge. Hydroxide is one of those special ones I told you to memorize, and it's OH with a -1. So these are my 2 ions. These are their charges. I only need 1 iron, but I'm going to need 3 hydroxides. This is where the parentheses will come in. I can't just put a 3 after it. If I just put a 3 here, that just means 3 hydrogens. I have to write it like this so that I am saying I don't just have 3 hydrogens. I have 3 hydroxides. So it's kind of like math. This 3 distributes to everything in there. I have 3 hydroxide groups attached to this iron 3. Ammonium carbonate. Double polyatomics here. So ammonium's a polyatomic, NH4 with a +1 charge. Then you have carbonate, CO3 with a -2 charge. So I'm going to need 2 ammoniums and 1 carbonate. So if I have more than one polyatomic, I'm going to need parentheses around it. So you write it in parentheses with the 2 here, telling me I have 2 ammonium ions and 1 carbonate. I know it's a lot. Let's do a little learning check. There's aluminum. Well, you know what? I'm going to let you guys do these. Look at your, I think we'll leave this here. Look at your polyatomic ion sheet. Try to figure these out. When we are in the classroom, we will go over those. And when it comes to naming them, though, you're just using the same system, basically. The polyatomic ions have their own little names, so just name them what they are. So this is sodium, this is nitrate, sodium nitrate. Potassium sulfate, potassium sulfate. This is aluminum, this is bicarbonate, aluminum bicarbonate. Now, this is bicarbonate. Sometimes it's also called hydrogen carbonate, so things can get weird. And let's see, do we want to do this here in the class? We might save these for the classroom. When I see you in class. Definitely mix practice in class. So I'm going to put, I'm going to put those up here. Pause the video, give them a shot, and then when I see you in class, we'll go through them. Here's some more. Oops, too far. Pause the video, give these a shot, see how you do, and that way you can come to class with your confused questions, and I will hopefully be able to help you understand it once we go through them and practice them in class. Whew, that was a lot. Good luck, and we'll do covalent next time. You all have a good day.